Okay, guys, again, if you're not already there, you are looking for this Unit 2 quiz results in Schoology. It's the last thing inside the Unit 2 folder. You should see a Google Sheet in there, and you can click My Document to open it. I would recommend opening it in a new window rather than trying to look at it in the Schoology window, just because it gets really cramped. When you open it up, it looks something like this. This is I just picked, this is actually somebody in this room, this is their paper, but I made it so you can't see their name. Anyway, this is somebody's paper who had Form A, who got an 83, and you can see their answers to each question and whether they got them right or wrong, along with the image of their form, which they had A. So again, if you didn't have Form A, yours is going to have a different one there. But this is how you can go through to see which ones you got right or wrong. So like, for example, they can see number 2 right there, but if they wanted to see what they did wrong on number 11, they would have to use this little drop down to skip ahead, and it must be on page 4. And so then they could see, oh, there's number 11, which we'll talk about in a minute. So anyway, this is the same way we did this last time, so it should look pretty familiar. But I would like to work through some of these questions because, again, you do have a test tomorrow, and some of you did well on this quiz, some of you did not so well on this quiz, and so I imagine that that some of you probably want to see what you did wrong so that you don't make the same mistake tomorrow. It's one thing if you make a 53 on a quiz because it's a daily grade. It's a different thing if we make that on the test. So we want to make sure that we get that taken care of before your test tomorrow. I would recommend that you take out paper as we go over this so that you're able to jot down any notes that you might need to for things that you missed. Now, if you did really well on this quiz, there were people who got 100, some of them in this room, then you may or may not really want to spend the whole period going over a quiz that you got 100 on. You may have a question or two, who knows? But if you're welcome to listen along listen as I go through it. But if you are in a spot where you're like, you know what, I did good on this, I feel good, I would rather use this time to work on my unit summary for some more practice, that's fine too. However, if you didn't do very well on this quiz, I'm going to very strongly suggest that you listen as we go over the quiz. Speaking of the unit summary, there was an issue with it saying to enter your ID on some of the question feedback. That should be fixed. I went through everybody who had opened it, so that should be working correctly now. But the unit summary is a daily grade redo. If your quiz was a 53 and you don't want a 53 in the grade book, do the unit summary and it will count up to a 70 as a redo for whatever your lowest daily grade is. If it happens to be this quiz, it'll replace it. If it was something else, it'll replace that instead. But if you need a daily grade redo, I'm going to very strongly encourage you to work through and complete the unit summary. Hopefully you already started it. It's been there since the beginning of the unit. But if not, that would be a good thing to look at tonight, not just because it is a redo grade, but because it is a really good review over everything we've done so far. So it's also a good test review. So if you are looking for additional resources, I'm going to encourage you to take a look at that. All right, so I am going to work through Form A with you, and so that's what I have on my screen right now. If you did not take Form A, you still have the same questions, they're just in a different order. You're going to want to skip around. And we'll go through these one at a time. If you have questions, you can ask. But again, hopefully by the end of the period today, you feel much more comfortable with these types of questions and feel ready for your test tomorrow. Number 1 on Form A is this question right here. It says a car accelerates from rest at a rate of 6 meters per second squared for 4 seconds. What is its final velocity after 4 seconds? This is obviously a calculation problem. And so we are going to want to start with all of our calculation problems by labeling the information that we've been given in the question so that we can go through that guess method, that process of solving these problems. So that's what we're going to do. Now, by the way, most people got this question right. 80% of you guys got it right. But I'm going to go ahead and label my given information, starting with the fact that I see that this car accelerates from rest. That's information that they're giving me. It's not a number, but it is a number. because if it says from rest, that's telling me that I have a velocity of 0. And specifically, this is an initial velocity because it says it accelerates from rest, and it asks for the final. So I'm going to label this as VI equals 0. I also have this value here at a rate of 6 meters per second squared. If you weren't already sure, you can check the units. Meters per second squared is an acceleration unit, but hopefully you could tell by reading that that was referring to the acceleration. The time is also given to me in this question as 4 seconds, and we are looking for an unknown final velocity. So again, your problem-solving process starts here. If you label things, you can then take a look at the equations that I have up on my board. They're still here. They'll be there tomorrow too. And you can look for the formula that allows you to solve for final velocity when you know V, I, A, and T. Because I don't know delta x, I'm going to avoid equations that have delta x in them, because that means that I wouldn't be able to solve for VF. So if I look at the equations up there, the one that I'm going to use is actually the first one. So the E and guess method is equation. We're going to use VF equals VI plus A times T. And so we're going to substitute into that equation. Again, you don't have to write the word guess on your paper. You can just go through the process, but I would strongly encourage you to go through this process every time you're doing a calculation. Plugging in, I have VF equals 0 plus 6 times 4. Of course, if I add 0 to anything, that's not going to change that number. So VF is really just 6 times 4, which is 24 meters per second. The answer to number 1 should be A, and as I said, 80% of you guys got this right. Does anybody have a question about number 1? No? All right, let's look at number 2 then. Number 2 on Form A is this graph question. So again, if you don't have Form A, you're looking for this giant graph. It is a velocity time graph, and it says, what is the displacement of the object whose motion is depicted by the following graph? Again, if you have a velocity time graph, you are going to determine your displacement by finding the area under your curve or line, in this case, on your graph. The area is always between the x-axis, which on this graph is down here. We've done this so many times. Some of your examples in your problem sets have the x-axis at the top, so make sure that you do pay attention to the numbering on your y-axis. But here's my x-axis, and so if I'm finding the area, I'm finding the area of this trapezoid. It's kind of weird, irregularly shaped trapezoid, and so that's not something I want to find the area of. Instead, you can break it into more regular shapes, which would mean that I can break this into a triangle that is sitting on top of a rectangle. Okay, and I know the equation for area of a triangle. It is 1/2 base times height. So let's go ahead and see if we can figure out what the area of this triangle is. Okay, and then we'll find the area of this rectangle, and then we can add them together, and that total area will represent my displacement for this entire 9 seconds. All right, so 1/2 base times height. My triangle has a base that is 9 seconds, and it has a height of, well, it goes up to 4, but the height isn't 4 because my triangle starts at 1. So make sure that you're careful right here. The height of my triangle is 3. So this is going to be 1/2 9 times 3, okay, which is half of 27, which is 13.5. Do the same thing with your rectangle, except of course area of a rectangle is length times width. The length of this being 9, the width of it, again, use your axes and use the numbering as 1, so that's 9. And so you're just adding 13.5 plus 9, okay, which is going to give you 22.5. So the answer to number 2 should be C. Number 2, 60% of you guys got this right. This is campus-wide. This period might be better than that. I don't know. Yes, we were higher than that, but 65%. And by the way, number 1 for y'all was 96%, so you guys did pretty good. All right, questions about number 2. All right, number 3. Again, Form A, number 3, is about an engineer designing a runway for an airport. You guys have seen this question before because you had one just like it on your problem set. It says an engineer is designing the runway for an airport. The planes that use the airport will start from rest and accelerate at a rate of at least 2.4 meters per second squared. The takeoff speed for this plane will be 60 meters per second, assuming minimum acceleration. What is the minimum length of the runway? So you have information given to you here that you can tell, hopefully you can tell by looking at this, that this is going to be a calculation problem. And so let's go ahead and take a look at our given information and see what we can label to solve this. The first thing that I see is that these planes start from rest, and so I see that I have an initial velocity of 0 meters per second. I also see that they have to accelerate at a rate of at least 2.4 meters per second squared. Sorry, this is taking a second to focus. So they give me the acceleration of 2.4 meters per second squared. And then they say that the takeoff speed, which will be your final velocity, is 60 meters per second. And they want us to find how long is this runway. What's the displacement of the plane going to be when it reaches the end of the runway? Okay. So, again, if you've labeled them, you can now take a look at your list of equations, and you're trying to find an equation that allows you to solve for displacement when you know VI, A, and VF. And there's only one formula up there that allows you to do this in a single step. It can't have time in it, because I don't know that. So that eliminates a bunch of them, except for one right off the bat. And so the one you have to use is this one. VF squared equals VI squared plus 2A delta X. Okay, that's the only one that allows you to solve it in a single step. So if we plug in, that is 60 squared equals 0 squared plus 2 times 2.4 times delta X. 60 squared is 3,600. 0 squared is 0. 2 times 2.4 is 4.8. All right, from here, of course, adding 0 to anything doesn't do anything. So I have 3,600 equals 4.8 delta X. We're going to divide both sides by 4.8 because our goal is to get this by itself. Okay, so 3,600 divided by 4.8 is 750, which makes the answer to number 3A. Does anybody have a question about number 3? About 80% of you guys got that question right. Let's see, what was the campus? 74, so better than that. Okay, number 4. Number 4 says, if a car moves with a constant speed, does it necessarily also move with a constant velocity? This question overall for the campus, 70% of people got this right. I would have thought it would have been a little higher than that, but it was okay. But ours was kind of right there with the average, a little less actually for this one. This is just a definition, okay? So this is something, if you don't remember it, you can write it down right now in whatever notes you're taking. But speed is scalar, which means that the direction that you're going doesn't matter. Velocity, on the other hand, is a vector. So yes, it is entirely possible to have a scenario where your velocity changes, not because you change the speed at which you're going, but because you turn. Okay, and that would mean that you still had a constant speed, but you no longer have a constant velocity if you are turning, because that means your velocity is changing and therefore you are accelerating. And so the answer to number 4 should be answer choice D. No, because the direction of velocity can change with constant speed. It's possible for you to ride a bicycle at 6 miles per hour and turn and stay 6 miles per hour the whole time, but if you turn, you have accelerated. Okay, you have changed your velocity. It's a vector. So just make sure that you know that turning is accelerating. Questions about number 4? Again, if you need to write that down in some notes, do so. If it's on your test tomorrow, I don't want you to miss it again. All right, this was one of the most missed questions. Maybe it was the most missed. Let me look. Number 5 on Form A. No, it's not the most, but it is one of the most missed questions from yesterday. So again, chances are if you missed something, this is one of them. As a campus, a little, like 42% of people got this question right, which means most people missed it. It says, use the VT graph below for the next 2 questions. Which position time graph shows the same motion as the VT graph above? Guys, this is a graph match. It might be a little bit of a more complicated looking one maybe than some of the ones that we did, but it's the same principle. And you're going to have to do this on your test. In fact, you're going to have to be able to draw this, not this one, but draw graphs on your test to make them match. Okay, I told you your test has free response questions. I'm telling you, you better look back at the graph match stuff and be comfortable drawing them. Look back at that assignment, that quiz, and the card sort, or the notes, because you've got to be able to do this, and this is definitely something that people struggled with. So again, when we look at this VT graph, quick recap of rules for VT graphs. I can tell by looking at a VT graph if I'm going forward or backward, not by looking at the slope, but instead by simply looking at whether my graph is in this positive region here, okay, in which case I'm going forward, or if it's below the x-axis. So above the x-axis means forward. Below the x-axis means backwards. Okay, these are all positive velocities, forward, negative velocities, backward. Of course, if you're at the x-axis, you are at rest, at least temporarily, or maybe you're sitting there. Okay, and depending on the graph. So again, whenever I look at this, some people in my last class thought this part was backwards. That is not what that means. This object is going forward at the beginning with some amount of velocity, and that velocity changes to 0 right here. So that means this object slows down while moving forward until it not just stops, but actually turns around and starts going the other way. Okay, so that's what's happening here. We move forward, we slow down to a stop, and we turn around and we move backward. Okay, and we speed up backward until we get to this faster velocity. Again, there's no numbers here, but then we stay at a constant backward velocity before, again, slowing down to a stop right there, and then turning around again to speed up in the other direction. Okay, so we're looking for that same type of motion on an XT graph. Okay, so on an XT graph, the way that I know if I'm moving forward, because the first part of this graph needs to be moving forward, okay, the way that I know that I'm moving forward on an XT graph is by looking at the slope. A positive slope on an XT graph means forward. So this right here, that's not forward. This cannot be your answer. Okay, if you look at the other options, all of the other 3 show a positive slope initially. Now, they start at different places, but I don't know if you remember me saying this about 4 times. You can't tell when you look at a VT graph where you start. So I can't use this to help me eliminate anything because I actually don't know where it starts unless it tells me. Okay, so I'm not worried about that, but these do all start out with a positive slope, and so they're all possibly the graph I need. Obviously, only one of them is, so let's look at what else happens. So it needs to go up, start out moving forward, but it needs to slow down and turn around. Okay, and so my slope, if I turn around and I start going backwards on my XT graph, again, slope is velocity. So this slope, positive means forward, positive means forward, positive means forward, but I need it to go and turn around and start going backward, which means I need it to get a negative slope. This one doesn't ever turn negative. Can't be my answer. It doesn't show it go backwards at any point. This is forward the whole time. It kind of stops maybe, but it's positive the whole time. Same thing with this one. Process of elimination leaves us with only one choice, C. This object moves forward, slows to a stop about right here, the top of that curve, and then starts moving backwards where it has a negative slope. And then it does it again. It stops here and then starts to move forward where its slope changes again. Okay, so that is exactly what was described here. Okay, they do match each other. The answer to number 5 is C. Does anybody have a question about number 5? Again, some of you may need to go back and review the notes on the graphs and how to tell which way it's going. Again, VT, you can tell if it's up here, it's forward. If it's down here, it's backward. XT, you have to look at the slope. Positive slopes are forward, and then negative slopes are going to be backward. Okay, you have to look at that. So you may need to go back and look at the notes or look at the card sort, but look at something. Okay. This question also is attached to that same VT graph, and this time we're going to match it to an acceleration time graph. So that initial VT graph that we had, I'm going to redraw it because we can't see it. It looked something like this-ish. Okay, not perfect. It doesn't matter if it's perfect, but it looks something like that. Okay, so that's what we're trying to match our graph to. So which acceleration time graph shows the same motion? Again, acceleration time graphs and VT graphs are the easiest two types of graphs to match to each other. Okay, and I said this in the card sort as well. All you have to do to figure out your acceleration when you look at a VT graph is look at your slope. Acceleration is slope on a VT graph. Okay, so looking at the slope of this segment right here, it has a negative slope. And so this AT graph needs to show negative acceleration at the beginning. This one's negative at the beginning. This one's not. That can't be it. This one's negative at the beginning. This one's negative at the beginning. Okay, so it's not B. It's either A, C, or D. Okay, but my slope here isn't negative the whole time. It changes. And right here, my slope is 0, meaning I have constant velocity. I have 0 acceleration. This one doesn't ever show the acceleration change. Okay, if I had a graph that looked like this, my VT graph would have to just be a straight line that never changed its slope, and we don't have that, which means it's either C or D. Now, my graph C shows a situation in which because there's a curve here, it implies that the slope would have to be changing, meaning that I wouldn't have a straight line like this. Okay, we're never going to have a curve on our AT graph. Okay, and we've never have had one on our AT graph. That's not going to be your answer either. It doesn't show the same thing that this does. This shows constant negative. It doesn't show a changing negative. Okay, this shows constant negative, 0, constant positive. And look at my slopes. Constant negative slope, straight line. 0, constant positive slope, it's a straight line. The answer to number 6 should be D. I just realized y'all couldn't see what I was doing. Okay, but there's my constant negative, my 0, my constant positive. Questions about number 6? 70% of you guys got that one right, or at least overall for the campus. For us, it was 75. All right, number 7. This, I think, was the most missed question. Let me look. Nope, for y'all it was 8. All right, but this was the second most missed question. It says, consider the position versus time graph shown below with 8 points on the curve marked. Read the statements about some of the marked points below and choose the most correct statement. And so we have some options here. We're just going to read through them one at a time and see which one is correct. So A says the object slows down from point 4 to 5. So just real quick, it says it up here, but this is a position time graph. Make sure you know what type of graph you're looking at. Okay, so object slows down from 4 to 5. Here's point 4, here's point 5. I don't see slowing down here because remember, on a position time graph, slope is velocity. Again, you have to remember that. Okay, if it's position time graph, slope is velocity. And my slope here, it looks pretty straight, which would mean I would have a constant slope and thus a constant velocity, meaning I'm not slowing down. Remember, slowing down or speeding up, acceleration on a position time graph means you have to have a changing slope, and that's going to look like a curve. Okay, and I don't have a curve here, so it's not going to be A. B says acceleration is 0 at points 3 and 6. So at point 3 and point 6. Well, guys, points 3 and 6 are on the curve. They're definitely not going to have 0 acceleration. If you're on a curve, you are accelerating. That's why the line is curving. Okay, and so this is not going to be your answer either. But what is happening at point 3 and at point 6 is the velocities are 0. Not the accelerations, but the velocities. And the reason why is because this object starts moving forward, and right here, it turns around to move backward. That's the point at which it completely stops while turning around. Again, it's the example of throwing a ball up in the air, and when it reaches the height, max height, it stops for an instant so that it can turn around and fall back down. That's analogous to this point right here. Okay, so it is a velocity of 0. If you're at the very top of the curve on a graph, or the very bottom of a curve like this one, okay, that's where the direction's changing from one way to the other way, and at that point, your velocity will be 0. The answer to number 7 should be C. But I'm going to go ahead and talk about D as well. D says acceleration is positive at points 1 and 8. Point 1, that's a straight line. There is no acceleration there. Point 8, same thing. Guys, if you hadn't paid attention and you thought this was a VT graph, it's very easy to pick D, because that would be what it would look like. If this was velocity time, yeah, you would have positive acceleration at those points, but this isn't a VT graph. Same thing here. If this was velocity time, you would have 0 acceleration at those points. So make sure you pay attention to what type of graph it is. Given that this is a position time graph, the only acceptable answer here is C. Velocity is 0 at points 3 and 6. Does anybody have a question about number 7? No? At least not right now? All right, let's go ahead then and take a look at number 8. Number 8 was the most missed question in this class period. I don't think it was for the campus, but you guys had trouble with this, and this is one of those things I told you was one of the most common misconceptions, which means we need to go back and look at some of those misconceptions that we started with. Okay, we're actually going to talk about this question after lunch because your bell is about to ring, but this one was the most missed, so we'll cover it whenever you guys get back from lunch. If they have the same sign, you are speeding up. I don't have that here, I have opposite signs. So right off the bat, you can eliminate B and you can eliminate D because it can't be speeding up. Okay, this has to be slowing down. Some of you, again, fell for that very common misconception of positive acceleration means speeding up. No, it doesn't, okay? Positive acceleration does not mean you are speeding up. It means the change in your velocity is positive. It could mean you're speeding up, but it could mean, in this case, that you're slowing down. Okay, you have to take into account both what direction you're going and if you are speeding up or slowing down in order to determine if your acceleration is positive or negative. Okay, so we have two options left. We know that we're slowing down, and in this case, the direction that you're moving in the positive versus moving in the negative, is solely determined by the velocity, the sign of the velocity. This is a negative velocity, and therefore they are moving in the negative direction while slowing down. That is answer choice C for number 8. I went over this because this is one of the most common misconceptions. We had it in the notes multiple times, but I'm going to go ahead and do it again. Okay, you can add this if you're taking notes right now. You can add this to your notes. I'm going to make a little table of times and velocities. And we're going to say, let's say that you have an object, and I'm going to do the same scenario, that's moving at, let's say, -8 meters per second initially. And after 1 second, it's moving -6. And after 2 seconds, it's moving -4. And after 3 seconds, it's moving -2. You get the idea. Okay, this object is moving backward. Negative velocities means it's moving backward. Okay. However, this object, what is its change in velocity each second? +2. This object, it has a positive acceleration while moving backward, and guess what? It is slowing down. Okay, ignore the sign, just look at the numbers. If you go from 8 to 6 to 4 to 2 meters per second, you are getting closer and closer and closer to 0. You are slowing down. The negative is just a direction. You're slowing down in that direction, but you're still slowing down. Okay, so you're moving in the negative direction, but you're approaching 0 for your velocity. So again, this is the same scenario this describes, an object with negative velocity and positive acceleration. Or perhaps it would have been easier for you to visualize it on a graph. You can always sketch a graph out. If you have a VT graph and you wanted to show this scenario, negative velocity, positive acceleration, it would look like this. Okay, I have a negative velocity because I am in the negative region of my graph. So I have backward motion here. Okay, but the slope of that line is positive, and the slope of my VT graph is my acceleration. And notice it's slowing down because it's getting closer and closer and closer to 0. If you need to go back and look at the notes again, do it. But I had this in the first few days of the notes because I said this is a very common misconception. Some of you are going to miss it on your test. Hopefully fewer of you now, but since we're going over it again. But please go back and look at it because it's something that students miss every single year, and it's really not super complicated. It's really easy to confuse it. Okay, so look back at those notes if you need to, or hopefully you took down some new notes. You can look at those tonight as you're studying, but please don't miss this on your test tomorrow. Okay, make sure you're making those corrections that you need to in order to not make the same mistakes tomorrow. All right, number 9. Number 9 was not much better, according to this, and I think I know why. The question says, a maglev train accelerates at a rate of 1.37 meters per second squared. Accelerating from rest, it can reach its top speed in about 82 seconds. How far in kilometers has the train traveled in 82 seconds? Okay, and if I approach this, or as I approach this calculation problem, we're going to do the same thing we've been doing, and that is labeling the information that we're given in the question. I have an acceleration of 1.37 meters per second squared. I know that it's accelerating from rest, which means it has an initial velocity of 0 meters per second, initially at rest. It can reach its top speed in 82 seconds, that's a time. And we're looking for how far does it travel in that time. So here's where some of you probably missed this question. It says how far in kilometers is it going to travel in that time? And yet the only unit that I see is meters. So we are going to solve this like normal. However, your answer when you get it at the end of the calculation will be in meters, not in kilometers. You have to do a conversion at the end, and that's the step that a bunch of people missed. Okay, don't do that tomorrow. Check your units. Okay, make sure that they match. All right, so if I want to solve this, I have A, V, I, T. I'm looking for delta X. If I take a look at the equations on my board, only one of them allows me to solve this problem in one step, and that is this one. Delta X equals VIT plus 1/2 AT squared. I don't want an equation with VF in it because I don't know what VF is. Okay, and this is the only equation that doesn't have it. All right, if we substitute in, we get 0 times 82 plus 1/2 times 1.37 times 82 squared. This will be 0, and we're adding it, so adding 0 doesn't do anything. I can get rid of that. So now we just have to do the rest of it. 82 squared is going to be a big number. Let's see, 82 squared, and then half of that, and then multiply it by 1.37. And that gives us this. Delta x equals 4605.94 meters. Okay, so if you selected answer choice B, you did all of the math right. What you forgot to do was pay attention to that unit. Okay, so what you need to do now is you need to convert this into kilometers. There are 1,000 meters in 1 kilometer, so basically you're just taking this number and dividing it by 1,000, which is going to give you 4.60594, or rounded 4.61 kilometers. Questions about number 9? If you had thought about it, hopefully you would have realized that that number is that's a ridiculous distance for 82 seconds. I mean, maybe you would have, if you thought about how long 4,606 kilometers is, it doesn't really make sense for something to travel that far in 82 seconds. Just from that standpoint, maybe that helped, I don't know. But just double check your units. All right, number 10. On Form A says, assuming minimal air friction, how fast will an object falling from rest be going after 5.5 seconds? So this is a calculation. It's a free fall calculation because it says an object's falling from rest. So let's go ahead and label the information that we know in the question. We know that this object fell from rest, which means it has an initial velocity of 0 meters per second. We are looking for how fast it's going after 5.5 seconds. They gave us a time. Okay, and again, we're looking for the final velocity. So right now, it doesn't look like I have enough information because I only have 2 things labeled, VI and T. I can't find VF. I need something else. What else do I know? Acceleration is due to gravity. I know that. Okay, so even though it's not in the question, and it won't be, you need to know this number, negative 9.8 meters per second squared. Every time if you have a falling object. Okay, all right, so I have VI, T, and A. I'm looking for VF. If I take a look at my equations, I'm going to choose the first one. VF equals VI plus A times T. And we're going to substitute in VF equals 0 plus negative 9.8 times 5.5. Of course, if I add 0, that's not doing anything. So it's really just negative 9.8 times 5.5, which is negative 53.9 meters per second. That's the final velocity. The question doesn't actually say what's the final velocity. It just says how fast, which is why the answers are all given in magnitudes instead of with the direction, because it's giving speeds. But it's still the same number. So you should have put B, 53.9 for number 10, and 85% of you guys got that right. So almost everybody did that one correctly. Actually, for this class period, nobody missed it. Every single one of you guys got that right, so good job. Because I was looking at the whole campus data. All right, number 11. Now, number 11 was actually the most missed question. However, we chose not to count number 11 as one of your quiz questions, and instead it got counted as bonus. So on your sheet right now, I don't know how it displays for you guys. It may, I don't know that the key part works because it's in there as bonus. But it's already in your grade like that. But the reason we did that is because only 10% of people got it right. So very few people benefited from it, but there were a handful that got this one right. And if they did, they got 4.2 points or something added onto their score. But most people didn't get it right, and it did not count against you. The quiz was scored out of 12 instead of out of 13. Okay, if you're trying to figure out why your grade looks like it does, that's why. So this one says, 2 balls are dropped from the same height 1 second apart as shown. Choose the most correct statement below. And overwhelmingly, you guys chose A. The distance between the balls always stays the same. And you ignored the graph entirely, I guess. I put it there for a reason. You could use it. You mostly didn't, and so you got it wrong because A is not the right answer. Okay, I'm telling you 90% of you guys put A. So let's talk about how we do actually answer this question, because it's not A, and I'll prove it to you in a second. Okay, if we look at B, the distance gets smaller and smaller until the second one overtakes the first one. That doesn't even make sense. They're both going to be falling at the same rate, so that would not happen. Let's look at C. The distance gets larger and larger. Okay, we can prove if it gets larger and larger by looking at this, because on a velocity time graph, your area is your displacement. So all we have to do is look. Let's take a look at what's happening at a time of 1 second. Okay, so at 1 second, there are two balls here. So the first ball, ball 1, I just realized that's too high, you can't see it. All right, ball 1, ball 2. All right, the ball 2 at 1 second is at 0. That's the point at which it's dropped. Okay. Ball 1, the first one that gets dropped here, after 1 second, it has traveled whatever that area is. Okay, 1/2 base times height, that's 1 in 10, so half of that is 5. So it has fallen 5 meters. So they're 5 meters apart after 1 second. Let's see how far apart they are at any other time on the table. Pick a different time. Do the same thing. Let's do 4 seconds, although you could pick any time. But let's see how far apart they are here. I'm going to find the area of both of these separate triangles. I have a triangle here, and then I have a bigger one that goes down here. Okay, so let's go ahead and find the area of this one first. This is ball 2. It's the one that was dropped second. Area of a triangle is 1/2 base times height. The base of this triangle, actually this base is from 1 to 4. So it's actually only 3 across. Half of that is 1.5. 1.5 times the height of this one ends here, which is 30. Oops. So 1.5 times 30, or half of 3 times 30, is 45. Okay, so that is the position of ball 2 at 4 seconds, is 45 meters. Okay, ball 1, first one that got dropped, half of 4 is 2, and then this height is 40. 2 times 40 is 80. So at 4 seconds, and again, you could have picked any other time, you just need to be able to compare two of them. They started out 5 meters apart, and then after 4 seconds, they are now 35 meters apart. They're obviously getting farther away from each other. Okay, and so that proves this one. The distance between the balls gets larger and larger, and you can see that with the areas of the triangles, just eyeballing it. You should be able to see that. But even without that, you could pick any two of those times and prove it with the areas. But yeah, because that first ball has already accelerated for 1 second longer, that means it's moving faster, and that's even greater distances, and then that keeps exponentially, whenever you look at the graph, it looks like a curve. It's not increasing linearly is the point, okay, because it's accelerating. So anyway, the answer to this one is C for number 11, but it did count as bonus points. It's already in there, and I don't think it marks it right on the sheet because of that, so just a heads up. Any questions about number 11? Okay. But yeah, if you have a VT graph, guys, and you're asked about how far things are, find the area. Don't forget about that. All right, number 12. A ball is thrown straight upward with a speed of 16 meters per second. Which statement or statements is or are true of this ball? So let's just read through these statements. The first one says the velocity of the ball is 0 meters per second at max height. That is absolutely true. We've talked about that already. If you throw something straight up in the air, it's going to slow down, slow down, slow down. It's going to stop while it turns around. So instantaneously have a velocity of 0 at max height. That is a true statement. So number 1 is good. Number 2 says the acceleration of the ball is 0 meters per second squared at max height. And that is not a true statement. Guys, if it wasn't accelerating at max height, it wouldn't turn around. If your acceleration was 0 at max height, then the ball would just sit there, motionless, like Wile E. Coyote does in the Roadrunner cartoons, if y'all have seen those. Okay, because there wouldn't be a change in the velocity. There is acceleration the entire time something is in free fall. Okay, from the moment it leaves your hand to max height to the ground again. Okay, anytime it's not experiencing any other force, the acceleration acting on that object is negative 9.8 meters per second squared. It's not zero anywhere. Okay, so this one, don't want to pick that. The next one says the velocity of the ball is negative 9.8 meters per second 1 second after reaching max height. And guys, this is the definition of acceleration. If something accelerates at a rate of negative 9.8 meters per second each second, and at max height, it has a velocity of 0, then 1 second later, by definition, it should be moving negative 9.8 meters per second, because that's how much it speeds up in that second. So this is actually a true statement. It should be moving that fast 1 second after reaching it, because that's the rate at which it accelerates, is that much each second. So that is true. So 1 and 3 so far. 4 says the acceleration of the ball is positive 9.8 meters per second when it moves upward. No, it is not. Every position on that trajectory, no matter if it's over here, it doesn't matter. Pick a point. The acceleration at every single point is negative 9.8 meters per second squared. That's why it slows down when it goes up. That's why it speeds up when it goes down. If your acceleration was positive when it was moving upward, that object would not come down. It would speed up as it was going upward. That wouldn't make sense. Okay? So the only correct statements here are 1 and 3, which makes this one answer choice A. Does anybody have a question about number 12? How'd y'all do on 12? Ooh, y'all didn't do so hot on that one. Less than half of you got that right. Let's see. That's definitely worse than the campus was. I don't know what about that one confused you guys, but definitely take some notes down if you need to about this. All right, 13. A rock is thrown straight upward from ground level with an initial velocity of 8 meters per second. What maximum height does it reach? Guys, this is a calculation, and it's one you definitely want to know how to do, because you're going to have something like this on your test. Okay, I'm telling you now. Okay, I'm telling you, look back at your graph match. I'm also telling you, you better be able to do this type of calculation. So maybe write it down. Most of you guys did it right, though. Let's see if it was better than the campus. Yeah, y'all are apparently better at math than you are at the concept questions. So let's take a look at it. It says a rock is thrown straight upward from ground level with an initial velocity of 8 meters per second. So let's draw something. So here's my trajectory. We're going to pretend that's straight up and down. Okay, and it has an initial velocity of 8 meters per second. What maximum height does it reach? So it wants to know what its position is right here. Okay, it wants to know what height that is. So let's label our information that we know. I know the initial velocity is 8 meters per second. That is the only information given to me in this question, but it's not the only thing I know. What else do I know? Acceleration. Perfect. Acceleration, negative 9.8 meters per second squared. Okay, we're trying to find maximum height, so ultimately we're looking for displacement, but still, I don't have enough information. I need something else. I can't solve any of these equations if I only know 2 things. I don't know if you heard her, but she said, hey, the final velocity is 0. And it is. At this point, right here, at max height, your velocity is 0. You just told me that in this question, right here. Velocity is 0 at max height. So guess what? I can call that my final position. You can write V top if that makes you more comfortable, but whatever you want to call it. But that velocity up there at the top is 0. Okay, and so now, because I am finding the displacement of the ball described here, I'm looking for the displacement when it's 0, which means I'm looking for the displacement when it's right there, which is what I want. It's max height. Okay, so with that information, we can now solve this problem. If I take a look at my equations on the board, I'm looking for one with VIA, VF, and delta X. I don't really want to see time in the equation because I don't know what it is. Okay, I could find it, but I'd prefer to do this in one step. And the only equation that allows me to do it in one step is this one. VF squared equals VI squared plus 2 times A times delta X. So that's what we're going to substitute into. 0 squared equals 8 squared plus 2 times negative 9.8 times delta x. 0 squared is 0, 8 squared is 64, 2 times negative 9.8 is negative 19.6. All right. So now we just have to solve for this. Algebraically, we need to move 64 over here, so we're going to subtract it from both sides, and we get negative 64 equals negative 19.6 times delta x. And now I have to divide both sides by negative 19.6. Those negative signs are going to cancel, so it's really just 64 divided by 19.6. And when I do that, I am going to get a displacement of 3.2653, it keeps going, meters. Okay, and if I take a look at my answer choices, that is answer choice B, 3.27 meters. That is the height. Okay, now, it doesn't ask me this here, but I just want to do it, just remind you, because I'm telling you you're going to see this tomorrow. Okay, if I had asked you to solve for the total time that the ball's in the air, and we used these numbers to find time, would that be your answer? No. No. Because if we use those numbers to find time, you would only be finding the time for the first half of its motion. So remember, if you have something thrown upward and you're using the max height as your point, meaning you're using either the height of it or you're using a velocity of 0. If you're using that and you find time, that's only the time up to that point. You have to double it. Okay, don't forget. The same thing is true if I tell you, hey, this ball is in the air for 8 seconds. What's its max height? Well, you're not going to use 8 seconds for this point. You'd have to divide it by 2. Okay, so it's the same idea, but make sure that you don't forget to do things like that as well. Does anybody have any questions about number 13 or anything else about your quiz? Again, guys, you do have a test tomorrow. My recommendation to you, you can continue looking over this quiz, but if you're looking for additional practice, I'm of course going to tell you to check out the unit summary. Or you can continue looking back at those problem sets, but you do have a test tomorrow. So please make sure that you are preparing between now and then. Otherwise, if you don't, you really shouldn't expect your grade to change much. Remember though, the test has free response on it. I'm telling you, look at the graph match, look at the calculation we just did. Okay, look back at your problem set, some of those graphs. You're going to see stuff like that again tomorrow.
Is the test